little bit information about me. I'm working as staff engineer here at Tuyala, programming in Scala whenever it's possible, because we mainly use Java stack, but I try to inject some Scala everywhere. I mainly focus on distributed system development, building platforms with Smack stack and Hadoop. I got my PhD in computer science. It's semantic storage domain. It happened 4 years ago. So just for the record, I'm running a blog at datastrophic.io, posting relevant stuff on Smack stack and different evaluations of different distributed systems and algorithms. And there is GitHub repo where you can find a lot of materials and workshops and virtual environments when you can play with Mesos or Hadoop on your laptop and so on. So, all right, what are we going to talk about today? Basically, we would spend some time on overview of Smack stack and how you could design different architectures for your data platform, how all the components work together, how to properly structure it, what you should think about when you're building your data platform. The next two parts are mainly on internals and architecture of Spark and Mesos. So in Spark, it's quite popular. I don't think I can bring something new, so we will try to look deeper in how it works internally. And with this understanding, we could build better solutions based on Spark. And the second part of talk, it would be bigger related to Mesos, how it works, how it makes decisions on resource scheduling, what is framework, how frameworks are working on Mesos. And half of the talk is about Spark on Mesos, how it's deployed, why Mesos is most effective platform to run Spark jobs. So, all right, Smack stack. Nothing new here, just a short recap. So Spark is the main data processing engine in this stack. So basically, you can do any computational data movement with Spark. Initially, it's super good in iterative algorithms used in machine learning, but it also fits any data rotation or data transfer needs, any batch or stream aggregations, and so on. So Mesos is a lot of hype around Mesos right now, and it's getting used more and more. It's a cluster resource management system, which appeared initially to address problems in MapReduce architecture. And it started gaining popularity because it's not only a MapReduce engine for running jobs, but a universal platform for running any type of applications. So Akka is basically actor model implementation for GVM, containing a lot of models to make it a universal library to to implement your microservice architecture or make your distributed systems or stream processing system. It's used as a core of Spark. So basically, Spark is built on top of Akka, and a lot of design decisions is basically driven by Akka design. So don't need to talk a lot about Cassandra. So basically, it's good, it's big, it's fast. So yeah, whatever. And Kafka distributed commit log. Super reliable, built-in performance in mind. So what's the main point in this slide? That any of this system is kind of universal. So it can be applied for a wide variety of tasks and problems. So let's start with storage layer. So in Smack stack, main storage layer is represented by Cassandra. And it has a lot of benefits, like it's very good at handling writes. It has configurable consistency over availability in terms of CAP theorem. That basically means you can, on per query basis, configure your consistency expectations from the result of execution of this query. How much replicas should respond to your query to be sure that the write went properly. It's linearly scalable, which is really important when you start to see any problems with your amount of data or performance problems. You can just add a couple of nodes or like maybe many nodes and rebalance the cluster, and the data will be evenly distributed across it. It's not like that easy, but it's doable, especially when you use V nodes. it supports cross-data center replication. If you are a global organization, it's really vital. You can replicate your data across different data centers by means of Cassandra without any extra tooling. It has some latencies, but I mean, it's still at the start. It's really usable feature. And yeah, using the same feature, you can easily resize or cluster or migrate data. But these benefits come for their own price. So basically, Cassandra has a specific data model. It's a distributed nested sorted map, basically where a primary key defines the physical location of the row in a cluster. So no foreign keys or something like that. So no joins, etc. So it's designed for fast serving, but not for batch processing. So select star queries will take forever if you try to implement it on a large data set in one of your services. So ad hoc queries is poorly supported by Cassandra as well. I mean, if you want to run like some query on historical data, it will take quite a long time. So it leads us to the idea that we need some sort of distributed engine to process this data in parts and then to get the final result. And Spark is perfect fit for this problem. So here's an example of how we can do Lambda-style join of pre-aggregated data with raw data. So here, campaign table represents Cassandra table with roll-ups on campaigns. And here we have like raw events, and we do basically join on this and then group by. So it's hardly possible to do it manually in your own implementation, but Spark provides this possibility. And you can just basically use this implementation. It's Spark SQL, but you can use data frame or maybe pure RDD approach, which is basically the same. It's all translated into a set of RDD transformations, which we will cover a bit later. But that's basically it. You can do full SQL SQL compatible analytics with Spark on top of Cassandra. And this, yes?
So that means you're basically reading all data from somewhere and reading it to memory, and then you
basically yes, but it's called table scan. And Cassandra worker is, let's go to the next slide, yes. So we'll go through this. So basically, Spark worker will read a primary partition range of this data on one node, depending on your consistency level of your query. It will take this range from Cassandra node, scanning the whole row or set of rows, then apply set of transformations to this, and then do shuffle, and then it's sort of map reduce. So it's not data loaded, all data is loaded in memory, but in distributed manner, collocated on the nodes together with Cassandra. So yeah, continuing with that, the common architecture when you build your analytics platform on top of Spark and Cassandra is to keep your clusters for input data or input streams and analytics clusters separately. So this gives a couple of advantages because you can resize your clusters separately. Your load patterns are different for these clusters. You can use Cassandra replication mechanism, or you can use Spark jobs to move data, because depending on the amount of data, data is cached in a disk cache, and so Cassandra will not suffer from this big read from it, and you can do it with Spark. So moreover, analytics cluster could contain some additional data or maybe enriched events. And basically, when you run a lot of when you have a lot of users running queries against your cluster, you need maybe a bigger cluster, and you don't need this big for input data, but for analytics, you can scale it and grow it separately. So yeah, and Spark resource impact is limited to only one data center in this case. Or maybe you can have several analytics clusters. And as we started to talk about resources and Spark that needs these resources, how are we going to address the problems that we have multi-tenancy environment and we have a lot of users running their analytics jobs on a cluster. So we need some sort of environment for this. And here comes Mesos of SMAC. Mesos initially, so basically initially Spark was implemented as a test framework to verify Mesos capabilities for resource sharing. So Mesos allows fine-grained resource sharing between Spark and other applications because it's not only framework for like MapReduce or Spark jobs. It's more universal than Yarn. User can easily share resources with other Spark jobs. It's called a fine-grained mode. We will discuss it in great detail later. Yeah, as I said, Mesos is a like universal platform for running all kinds of applications. So anything which could be run with Shell or Docker could be executed on Mesos, or you can implement your own framework. It's built with fault tolerance and scalability, so you can add more nodes to cluster, remove nodes without any major failures of running jobs. It will be rescheduled until there is enough resources in the cluster. So here on a diagram, you can see that we have several Spark applications with schedulers and executors running on different nodes and sharing these physical nodes with different other jobs and frameworks. So coming to Kafka and Spark, here is an example of how you can build. Sorry. Here is an example of how you can build like a whole data processing pipeline. You have set of producers populating a Kafka topic with some data. Maybe there is some Spark streaming job which use time-based, like window-based aggregations for pre-aggregation or maybe enrichment of data coming in. You can publish it to another topic, which is then consumed by another Spark streaming job and written to Cassandra, or you can directly write to Cassandra. It depends on your use case. You can use a backup mechanism with Spark streaming as well to back up your data to S3, HDFS, or another Cassandra, or whatever. So the main goal of this slide is that like you can build whatever architecture you want with this stack. But building this, a couple of cases we face here in Yala is that we need to be prepared for failures upfront, and we work a lot on designing patching and failover strategies. So when we experience some failure in code, or maybe a broken data, or late data, or duplicated data, so we have a plan for running backup or patch job to fix this and to overwrite, or maybe move some data. Another point that if you are really worried about exactly one semantics, then the whole pipeline could guarantee you exactly one semantics with Spark streaming and Kafka, but you still need an idempotent store for this, because when you have duplicate write, it shouldn't affect the data you store in Cassandra. So basically Cassandra counters, for example, will not work well for this, or any incremental store. Another strong part of Spark stack is that it's super concise. So basically here is an example of job aggregating, so basically reading a stream of events and saving to Cassandra. So that's pretty much it. Just initialize connection to stream, to Kafka topic, map incoming data to internal event representation, which represent Cassandra table model, save to Cassandra, and that's pretty much it. How to ingest data in your system. There are a lot of ways you can you can go with any microservice architecture. As we are in the context of Smack Stack, Akka HTTP is a perfect fit for that, because it's like it's actor model. It's built in asynchronous. It enforces asynchronous message passing. Lack of shared state. It scales easily. If your services are stateless, it's perfect. You can easily, it's super easy to pack it in Docker and run on top of Mesos. So you can write directly to, Kafka or directly to Cassandra, depending on your case. Basically here for some time critical, like when we need real time, close to real time response times, we write directly to Cassandra and perform our own Lambda-ish architecture on top of it without using Kafka in front of it. So here is the complete microservice to receive some JSON data, parse it, and send both to Kafka and to Cassandra. So important part here is that we initialize a new actor, which is called Cassandra Writer, and send event to it. So that's basically it. What's missing here is that class declaration on top and close and brace in the bottom. So it could be packed and run. How we could run to Cassandra, write to Cassandra. Basically, we got event, create statement, specify consistency level. We use quorum, we can use any other consistency level, and execute in try catch, responding with write successfully if execution went good. So that's another example of conciseness of the stack and how is it easy. Yes?
Could you go over why you might choose using Okta versus Spark streaming to write to Cassandra?
Excuse me?
You gave an example earlier of using Spark streaming to write to Cassandra, and now an example using Okta. Like, what are the pros and cons of using?
Yeah, okay. So here you mean this one? Or?
Yeah, so before this you showed use Spark streaming.
Yeah, we consume from Kafka topic here and write to Cassandra. So basically, this is a kind of simple example of just consume and write. But in real life, you can enrich it or maybe aggregate on some time window to not overload your Cassandra and pre-aggregate data and then write to Cassandra. And as I said, it really depends on your case, whether you write to Kafka or you want to write directly to Cassandra, because it's not all data. It's not the same. All data is not the same. So some data is needed. Like it all depends on your use case. If you want to write to Kafka, write to Kafka. So this is just examples of how you can achieve both of these. So here, for example, a use case, I write to Kafka topic consumed by all other data platform systems. And I use Cassandra as a backup store for raw data, for example, to batch aggregate it afterwards and build a Lambda-style architecture. Does it make sense? All right, so here's an example how you can build Lambda architecture with Smack Stack. So for speed layer, we use partial aggregations in the bottom with Spark streaming and populate Cassandra with real-time views. This is exactly the example we saw before on reading Kafka topic and writing to Cassandra. And here, we use the same Spark streaming to write to Cassandra with raw data. And after that, we run pre-compute and batch job with Spark on scheduled basis and perform batch views, which is then read together with real-time views. So it's basically classical canonical Lambda architecture. But in reality, it's not always works this way. So it's when design meets reality, it's hard to implement it in canonical way. So it could be a bit shifted, or more components or more steps will pop up in this picture. Depending on your use case and retention in your Kafka cluster, you can easily implement Kappa architecture. But again, it depends on your requirements and how fast you want your data, what your expectations on this. So the main point again is that you can build whatever you want with Smack Stack if you have your clusters running and simple API how to use it. So finalizing Smack. So as I mentioned, so it's basically a wrap-up of all the points I mentioned before. So Smack Stack is a concise toolbox which allows you to build, to pick different parts of it and build and use only what you need to build your systems. It's easy to scale every part of it. And you can use Smack Stack as a single platform to build whatever application or implement different application designs. So if you have Mesos cluster running, so it's extremely easy, your time to market is extremely short because MVP verification or any prototype building without any complications, you can build whatever you want in a really short amount of time. So previously, I've been working as a consultant, and we've built in a one-man month. We built a working system based on Smack Stack for sort of ad serving, which worked before until now, more than a year without any changes. So I think it's a good timing for building a data platform. So it's just as a reference. So we are going to talk about Spark architecture in depth. So I think we could have a short time slot for questions. Or does it make sense? Yes, please.
What is Kappa architecture? Never heard of it.
Yeah, so basically Kappa architecture is, let's see here, maybe this one. So basically, in Kappa architecture, let's use this one. In Kappa architecture, you don't have the top batch layer. So basically, you operate on real-time views, incrementing this data, and when you building a unified view with one job over your data set, which is which lives in Kafka topic. And if you want another view or another like slice or representation of this data, you just execute another job in parallel, which reads the stream from the beginning and performs and builds this view for you. But this architecture is basically limited to the retention and like the storage size of your Kafka cluster. So that's basically it. But in reality, if you have a really huge amount of data which doesn't fit Kafka, so you will fall down to some sort of Lambda architecture when you pre-build some historical data and then you consume the stream again. But in fact, I'm not sure that, like it depends because when you do real-time analytics, you don't need yearly data, you need something on a short time period. Yes?
How do you get started with this Smack stack? Is there some set of Docker containers one can use?
I mean, yeah, okay. The easiest way, if you want to play a bit with Smack stack, you can set up. I will share some links with the Dockerized environment for this, and you can start. So basically, the entry point is Mesos cluster, on top of which you can run whatever your Dockerized applications, your Spark jobs, and you can even run Cassandra inside a Mesos. It's kind of like supervised by Mesos. But the easiest way to start depends on if you want to bring it to production. You need just to install it somewhere in Amazon. Or if you want to use it like company-wide. If you want to play and like figure out how it works, it's just you can build up Dockerized environment with Docker Compose. I will share some links on how it could be done. Yes?
I saw on your slide on you can write directly to Cassandra.
Yes, exactly.
I know Cassandra isn't good to have a lot of parallel writers.
Actually, it's not true. It's super good in this. It's when you do schema modifications in parallel, that's extremely bad. And
It's always bad.
yeah, because this system key space in Cassandra has specific replication factors, and you need basically all replicas, all Cassandra nodes to agree on the schema. And when you modify schema in parallel, they can't reach this agreement and go async, and it could ruin your cluster basically at some point. But multiple parallel writes, it's exactly the use case Cassandra good at it.
Okay.
So for example, we did some performance testing of our cluster. So our 5-node cluster with 8 core each node, it holds like 80,000 requests per second, inserts per second, with quorum consistency. So basically, we wait for acknowledge from 3 nodes. So we write to 3 nodes simultaneously.
Which amount of data per second is throughput?
It's basically our it's basically our model. It's like events, campaigns. It's not blobs. It's basically like you can imagine a data model for.
Small events, right?
Hmm?
Small events, not a huge events.
Yeah, not a huge ones. So, but we were replicating our use case. So it's basically you can imagine a data model for like ad serving. It's campaign event side. Basically, maximum 20 fields with UIDs. So that's the load pattern. But we were hitting different. We were covering different use cases when we write to one row in one node, and when we write to unique rows on multiple nodes and mix it. So and in the worst case, it was 80K writes per second. So it's in 5 nodes. I think it's pretty good. And actually, you can just kill one node, and it will drop down a bit. Then you bring that node down, a node back, and it's 80 again. So it's really reliable and really good holds like this writes. Yeah. Okay. Let's continue. Or any questions up to the moment? Okay. So who uses Spark in production? All right, pretty good. All right, for those who not, so Spark, yeah, why do we like Spark? It's super general. You can use whatever model for your jobs. You can use it for batch processing, for streaming with Spark streaming. Graph machine learning is super good in machine learning. Provides concise API for manipulating data at scale. As we saw some examples of like conciseness. This API provides a user with capabilities of management of data placement. So basically, you can control when you place your data in cache or when you persist it on disk or external storage. It's built in a bit different model compared to MapReduce, so it applies a set of quartz grain transformation over data chunks or partitions, and relies on lineage of computation to recover from failures. Yeah, it's initially it was built for Mesos, but it has standalone mode and integrates with Yarn. We will see differences later a bit. So yeah, Spark makes data engineers happy. So here are some examples of how can the first one, backing up and restore Cassandra tables in Parquet. Speaking about conciseness. So we read Cassandra table, map to our data model, transform to data frame, and write to Parquet to HDFS or S3. And the back way is restoring pretty same different order of lines. We use Spark for querying discrepancies in different data stores in our systems. So for example, here, the bottom example is we compare amount of counters in Mongo and Cassandra stores to identify discrepancies. So joining, so it looks really awesome when you can read data from Cassandra and join with data in Mongo in one query. So it's all about adapters and integrations. So core concepts of Spark, just as a recap. So Spark application usually consists of user program where user interacts with Spark context, which is created on a startup of the Spark driver. Spark context provides holds information about cluster connection. User creates RDDs interacting with context, applies set of transformations which introduce dependencies between RDDs and build another RDDs, which form RDD graph, which is then transformed to direct acyclic graph and scheduled by DAG scheduler into set of tasks which are executed via cluster manager on a set of workers. So we will revisit this moment a lot soon. But the initial idea is that the user code is translated into a graph of tasks, and which are then split into stages and run in a distributed manner. The core concept behind Spark is RDD, or Resilient Distributed Data Set. It's well known for those who use Spark. So basically, to shortly describe it, fault-tolerant, immutable parallel data structure, which provides API for data transformations and materializations, API for persistent data and for reuse, and partitioning data for optimizing data placement. It usually needs when you need it when you have super large input and you want to redistribute the data in the most optimal manner to optimize performance of your Spark job. RDDs are created from Spark context, either from reading from some external storage like database or a distributed file system, or from another RDDs. So basically, there is no other way to create RDD. RDD store information about parent RDD to recover in case of failure. It's called lineage. From a developer's point of view, RDD is an interface defining 5 main properties. So partition, a list of partitions, so basically splits in Hadoop or where partition data is stored, list of dependencies on other RDDs, and a function to compute each split. It's called a lineage, and another to Two optional properties is locations of data and a partitioner defined for this data. So basically for Hadoop it's hash partitioner. This information is used for execution optimization. So simple example, what happens when you do Spark context text file? So actually it's a bit tricky because initially it calls Hadoop file and forms Hadoop RDD, and it's a key value RDD which is then transformed to just values RDD, so it's like RDD of strings. So partitions of RDDs, it's HDFS blocks, no dependencies because it's the first guy and created from external store. Compute function is loading data block into memory. HDFS block locations as preferred locations and no partitioner. The next guy created with map function. It has different from parent is only compute functions, which computes parent, which involves parent compute functions and then applies map function to it. So one line with blocks transformation, it's pipeline dependent on dependency type of your operations, but we will cover it a bit later. So what types of operations are present on RDDs? There are basically two main types usually mentioned. It's transformations, which basically speaking, transformation introduce dependency between RDDs. It could be a function applied to every element in collection or some aggregate function or sort function grouped by. And repartitioning is usually referred as transformation as well. And some actions. So basically all transformations are lazy. When you write your Spark code, Spark job code, you apply a set of transformation on RDD. They are all lazy and will not be evaluated step by step. Evaluation of these operations are triggered by actions, which trigger actual job executions. So basically, amount of actions in your Spark application basically defines amount of jobs, which is a bit different. So basically, Spark application is not a big job. It consists of number of jobs. Yeah, so basically actions used to materialize results and they trigger execution. And you have some extra functionality on RDD, like store on disk and memory on off heap. Under off heap, we use basically only Tachyon is supported by Databricks, I think, or it's some Berkeley child. And you can use checkpointing to truncate RDD lineage when it's too big and it's too expensive to recompute. You can checkpoint RDD to HDFS, for example. So when it will fail or recomputation will be needed, it will be read from checkpoint. So basic execution workflow. When you have RDD graphs, RDD's graph, it's translated by DAG scheduler. The graph is split into stages of tasks. We will talk about this. And DAG scheduler submits each stage to a task scheduler, which talks to cluster manager and controls the execution of these tasks. So executor usually consists of thread pool, which handles each task in a separate thread, and a block manager, which controls the data placement, loads data in memory, or reads data from memory or external store or disk. Yeah. So basically, it's the same example we saw before in the SMAC part, which was Spark SQL, but this one is implemented with RDD API. We do pretty same. We read events, we read rolled up campaigns, and we join events with campaign, trying to get the same result. So basically, combined result in Lambda style. So hopefully it's working. So yeah, I have my virtual micro Hadoop cluster running, and I executed this code. And we see some different, we see different stages and different tasks and stages and different dependencies type between them. We are going to walk through this and to better understand what's going on here. Where is this? Sorry. It's really nice. Where's my slides? Yeah, nice. All right. So yeah, I would say that any data computation or any computation based on data consists of several main steps. So basically, as first step, data is loaded into memory or loaded from external storage or initial source or whatever. Then set of transformations applied to this data maybe taken into account, maybe joining this data with some other data to achieve final results, and then the final result is returned to user or persisted in external storage as well. So here we see different types of dependencies between steps when you produce RDDs. So we have shuffle steps. So if we take a look back here, so basically shuffle happens exactly here when we do reduce by key from initial code. Okay. In here we see copartition shuffle, copartition joint when no shuffle is needed. It happens when when source RDD and final and target RDD has the same amount of partitions and they have the same partitioner. So we will take a short look into types of dependencies to cover a bit how job scheduling works in Spark. So we distinguish two types of dependencies. It's narrow ones, which basically are applicable. Set of narrow transformations combined together to be applied as the whole, like a chain of functions applied to initial partition to form a final partition. So it's the main distinct thing of Spark compared to MapReduce, where each step is stored to HDFS. So here, the first one, which distinguishes Spark and makes it faster. So a set of operations which don't need shuffle, it's applied in memory on a memory basis. So basically, computations delivered to data in memory. So another, failure recovery is pretty simple because you need to read only the last partition before computational result is lost and apply the same computation, not to the whole data set, but only to one partition. So another type of dependency is shuffle dependencies. These are like bad ones. So that basically shuffle dependencies appear when source and target amount of partitions are different, or maybe more than one target partition depends on source partitions. Example of these operations are join with different number of partitions, or group by key, or basically all by key operations are introducing shuffle dependencies. In case of failure, it's pretty expensive to recompute them because all parent partitions need to be recomputed before to get the result. So not only one, because target partition combines data from all the source partitions or part of source partitions. So coming back to these pictures, so how stages are formed in Spark. So here we see like 5 stages, and let's look deeper in how they're formed. So when RDD graph is submitted to DAG scheduler, it goes backward from the final RDD to identify shuffle dependencies between RDDs. So any narrow dependency is pipelined into one task over partition, and when scheduler meets a shuffle dependency, so basically it's really good explained in source code of Spark, where there are different type of so basically there are different types of tasks, which is basically shuffle map tasks, which partitions input for shuffle and writes to disk, and result task, which is the last one, which returns result to driver or writes data into storage. And the basic breakdown strategy, so you have that many stages in your application. You have as many stages in your Spark application as many as shuffle dependencies. But as many shuffle operations you perform, as many stages you will have. Why should I care basically about this information? Shuffle is a pretty expensive operation. because network is not that slow nowadays as it was before, but the operation of consuming the shuffled data from different sources is pretty expensive because you need to consume all the data from chunks around the network depending on your cluster size and apply reduce logic to this data in some asynchronous and effective manner. So basically, it often requires a lot of memory on reduce side. And basically, that's the most error-prone part of all Spark jobs. So, and basically, main recommendation for this is try to limit the amount of data shuffled around the network before performing this transformation. So basically, filtering, mapping, and all the stuff should be done before doing any by key operations, or reduce by key should be preferred over group by key if you need to sum up all the data. It stopped working. Yeah, blue arrows here represent a single task within a stage. So you can follow the idea of how it's working. So yeah, I talked a lot about shuffle, so how it works in fact. So shuffle map task splits input partition into number of files, or it's number of files equals to number of reducers which will consume these files. It has been before Spark, until Spark 1.2, it's called hash partitioning. And shuffle reads basically reads each file from source executor, source worker, and tries to merge them in memory and apply another set of transformation on top of it, and writes the next set of shuffle files. So yes, and in latest versions of Spark, the default version of shuffle is sort shuffle. Basically, how it happens, the main problem with hash shuffle is that the amount of files is too big to be so basically to be read, and if files are small, a lot of network traffic and a lot of operations happen, and the network is overloaded and the reducers overloaded, and that's basically a small files problem. Partially depends on this, partially results in this. Sort shuffle is a bit different way of doing things. So shuffle map task consumes partition and try to sort record in memory to create a file sorted by number of executors with index which contains offset for each executor, for each basically reducer which will consume this file. So in this case, number of files is equal to number of partitions in your RDD. And if sorting doesn't fit memory, it will spill to disk and then merge it files into one. So it's way more effective, but still, if you have big partitions, it will take longer time. So basically, a basic recommendation on running this working with Spark jobs is that you have some sane amount of partitions in your application. So that's why you can use these additional API functions of RDD like repartition. Basically, if your executor hangs and dies with out-of-memory exceptions, it basically can be explained by this. So you should better maybe repartition or something like that. Main recommendation is to have something between 1,000 and 2,000 partitions, but it depends on your cluster setup and how many nodes you have. So basically parallelize as much as possible, but not too much. Yeah. Another interesting thing, which comes with tungsten sort, which is implementation Java library with different arrays implementation with which uses language primitives instead of boxed objects. Is that with cryoserialization you can sort RDDs, you can sort records without deserializing them. So it gives a lot of effectiveness if you transfer pretty simple data like numbers and strings. So you can sort RDDs without deserializing them, which offloads your memory pressure pretty much. But this leads to another interesting fact we faced during our work with Spark, is that sometimes duplicated data disappears So basically use case when you want to reduce duplicated key and sum up their values to filter out duplicates and reach consistent state. So basically duplicated values disappeared from after shuffle phase. So our idea is that this happened because of this super optimized shuffle sort. Yeah, quick look to Spark components. So as we've seen, a user program heavily relies on Spark context to negotiate with cluster and run its jobs. The Spark context contains task scheduler we discussed before. As a task scheduler is responsible for performing negotiation with cluster. Depending on implementation, it performs task scheduling. It talks to cluster manager. It could be standalone, yarn, or messes. And in most cases, except messes, it launches Spark executor and talks to it by means of its own RPC implementation, which is akka. So basically, executor is launched controlling with configured amount of memory and cores per executor. With yarn, you also limit number of executors in cluster because of specific architecture. And then task scheduler forms these tasks, which are pipelined per stage, and starts running these tasks, sending tasks to executors, controlling task status, and then when all tasks are finished, it reports to task scheduler, and task scheduler then executes another stage. So scheduler backend is basically responsible on how to negotiate with executors in a cluster. So we will cover method scheduler backend in more details in the second part of talk. So since Spark 1.6 memory model looks like that, before this it was more conservative with a lot of regions reserved and less freedom for user. So right now there is a reserved memory which is needed for running executor itself. And there is a user memory needed for user data structures, so user objects created. It acts as a safeguard against out-of-memory exceptions as well. So it's used to some memory stealed from there if something happens which is out of order during execution of computation. And the main Spark memory is split together. So it's 75% of the total memory of executor, or basically JVM heap because it's JVM process. And 75% is split into two halves. One half is execution memory, where basically all this shuffle and sorting happens, and storage memory, where cached RDDs are stored. When execution memory is not occupied fully, Spark can resize storage memory region to store more RDDs to optimize further computation and not to load data in memory again. But there is a safeguard value which is 50% of Spark memory, and below this value RDDs are never evicted from this cache space. So that's the main difference compared to previous versions of Spark. So yeah, it's pretty nice. Yeah, execution modes of Spark. So you can run Spark shell. It's simple REPL connected to cluster. So it's really good to testing and evaluation of your some of your code, or maybe you want to do some ad hoc queries. It always runs in client mode. We will cover it a bit later. And Spark submit is a script coming with Spark, which basically executes Spark job on a cluster, submitting it to cluster, and running a set of tasks, scheduling a set of tasks on in a distributed manner across workers. So basically, you can pack your jar in a fat jar and submit to Spark cluster with your entry point, and it will be executed. So basically, this is a common way of running Spark jobs. So Spark submit and Spark shell parameterized by master, which could be a local for testing. For example, you specify a number of threads, and local Spark like Spark shell is executed in local mode, where you don't have to spawn up all the cluster or some workers or any other process. It's a single process. Spark Master is for Spark standalone installations. It's pretty rare, I would say. So, and correspondingly, Mesos and Yarn. In Mesos, Spark will be run on Mesos, obviously, with different deploy modes. Basically, cluster mode, it's a bit tricky in Mesos because you need to run separate process in Mesos cluster to achieve this. So basically, client mode is the most common one and the most easy one without any drawbacks. And the same for Yarn. You can run in client or in cluster mode. The difference is that when you run in cluster mode, your driver program is executed as a separate Yarn container in a cluster, and your Spark submit script only receives updates from yarns that the container is running, but all the output will be stored in application container location on Yarn. But when you run in client mode, all the results are returned back to driver, and it starts working from the node you launched it. When to use each, I would say if you have some sort of super long running job, it's better to use cluster mode with Yarn, because when you execute it, you can forget about it, and in case of failure of your driver, it will be re-executed or rescheduled by Yarn on different node, on different container. So yeah, that's pretty much it. What time is it? It's 7, so okay, just to announce, okay, so it's time for demo. I think I would show some code, but for those who's eager about playing with Spark in different execution modes and different API, there is a GitHub project containing Dockerized Hadoop with Spark. So there is a pretty good README. You can play with it, launch your cluster, run some jobs, and so on. Try different execution modes. But so I think it's a good time for questions right now. And after that, we can do some demo. Yes, questions, please. Yes, please.
How do you monitor Spark?
Actually, we don't monitor Spark up to the moment because, like for our use cases, we use short running jobs, which we can wait until it ends, so it's pretty fast. But for there is a way to monitor it. You can basically introduce some Codahel library for metrics inside Spark and report metrics to a Datadog dashboard. Or if you have some long-running jobs like Spark streaming, you can create some sort of alerting based on pager duty or something like that. So basically, it's the way you monitor your Spark jobs is pretty same as you monitor your Java applications, because all you need to care about is your driver health, because the rest you have no control over executors. So, and actually, it's responsibility of a cluster manager to guarantee your liveness of the executors. So if your driver fails, that's bad. So you need to monitor driver. So that's basically it in driver. You can like make your checkpoints and send metrics to Datadog, for example, controlling, collecting different metrics.
It's on shoulders of Mesos, right?
Hmm?
It's more on Mesos' responsibility.
Well, yeah, I mean, Mesos controls the liveness of your executors, and and basically sharing the resources. But I mean, what you can control, so you can catch exceptions in your driver code if you run in client mode, and yeah, and it depends on what are you going to monitor. I would say it's not super common to put a lot of monitoring into Spark jobs, because it really depends on a lot of factors. For example, if you have 100 users running their Spark jobs on a cluster, you couldn't get any feasible information about like medium duration of a job or whatever, because it's like temporary. So basically what you need is to control your success or failure of your job execution, and it's pretty easy to do with any sort of metrics or reporting library embedded into your Spark job, into your driver code, basically into your application. So in the end, you can send like some health check is healthy or like in progress running. So it's a bit of duplication of cluster functionality, but it really depends on the use case. Any other questions? All right, so we have pizza right there. Thank you for your attention. And the next part would be about Apache methods. And we will continue after a short break. Thank you.